Right.
Okay, I'll start.
Yes, I think you can go ahead.
Okay, so this is the fifth session, and we are going to talk about the things that I haven't fully figured out yet. So the open problems in reverse physics. So this is going to be the session where we're going to be talking about quantum mechanics, thermodynamics, and all other neat things. So let's see if everything works. Where is my cursor? There it is. There you go. Okay, so first an overview of what the status is for all the sort of reverse physics approach for all the different theories. So for classical mechanics, as we saw 2 days ago, we are basically, I consider it done in the sense that we have the fundamental assumption. We can kind of reconstruct the things that we want to have. We have a very nice understanding of what the different geometrical objects are, how do they function, and what they mean physically. Of course, things can be always improved. So if people want to help improve there is always space. But to me, I'd rather start building the foundation for all the other for the approach on all the other theories, so that we can get sort of the whole thing moving. There always can be improvement. Improvement is always there. So classical field theory, instead, it's something that we really have no idea on the technical level how to proceed, and we'll see a little bit. We have vague ideas. We kind of have an understanding of what the pieces should be. It's just that on a technical level, it's unclear how to implement it, and we'll see that. In quantum mechanics, instead, I think the core ideas are identified. The last bit was that classical limit, and that really gives us confidence that really the only thing that changes is this lower bound of entropy, which basically means irreducible an irreducible system. There is a hole, but then the description of what's going on inside is below the threshold of what you can detect. So you can't get information about the internal structure, and that's where the cutoff for the entropy is. So there is a cutoff. Below that, you can't get any more information. So that's clearly understood. You just need to actually go through the motion and find all the equivalent characterization of all the different pieces and so on. So that needs to be done. Quantum field theory, it's again completely up in the air, and I'm not going to work on that until quantum mechanics is done and we know how to do classical field theory, because it's just going to be a mess trying to do quantum field theory, because we don't know how fields completely work, and how quantum mechanics should be like really, really nice and understood. So, which also means that quantum gravity would be even worse, because there is no theory yet, and the foundations of all this thing are not really well set up. So, but I'll talk a little bit of some idea of quantum gravity still, because it's just again, we know that some ideas that need and how they need to work, and so probably that extension is sort of the obvious thing. Whether it gives you quantum gravity or not, it doesn't really matter. We need some type of things to close the arguments. And then there is thermodynamics, which is in a state that it's a little bit similar to quantum mechanics. I would say a little bit worse. In the sense that we think the ideas are right, but there are some details that I still don't quite understand how they should work. But thermodynamics is a much simpler theory than quantum mechanics, so on that level is a little bit easier. So this is kind of the overview. So we're going to go through essentially all of them in an hour, and I'll have to go quick. But these are the type of things that if anybody is interested, we can have follow-up sessions, follow-up live, and start discussing and kicking ideas of how anybody can sort of help me move these things along. So let's start with classical field theory. And the study is basically, I'm looking for somebody to help me generalize what we have in classical mechanics to quantum field theory. And it shouldn't be conceptually that far away, because you have just to go from finitely many degrees of freedom to continuously many degrees of freedom. And so the main conjecture, in the same way that volumes in phase space, oh, a second, I forgot to, there you go, to light the other light. Okay, so the main conjecture, as we saw, volumes in phase space provide a count for the degree of freedom. Volumes in phase space provide a count for states and configurations. So we have this symplectic form that sort of does that solves that problem. And the idea should be that volumes in space should provide a count for the degree of freedom. So whenever you're counting degree of freedom, you're going to have a state density per degree of freedom, and then you have a volume of space that tells you these are how many degrees of freedom there are in this region, and all the count of states of deterministic irreversibility independent of the degree of freedom should basically be amended to do this. And so what we need is essentially to find a suitable Hamiltonian symplectic formulation of field theory. And it can even be sort of without general relativity, just on E and M. And I'm told that there are, well, I know that there are a couple of these things, and I looked at some of them cursorily, and they're different, like there are a few different ones, and so it becomes a problem of understanding which one is the one that actually works for us. And then this whole understanding needs to be connected to again, how to generalize Cantor state, entropy, and information entropy on a field theory. And even there, I haven't found a way to do it. I haven't found a standard. Oh, this is how you do information theory and a field theory. This is a space of field configuration. We put a probability distribution on it, and we define the super Shannon entropy because it has to be on done absolutely differently. And but what the assumption is here, the conjecture is that once you have made that connection, all the arguments that we had in classical mechanics are just going to transfer to quantum field to classical field theory, because that's essentially how things should be done. And so just to give you sort of an idea, we talked about the principle of least action as being as the variation of the action being the flow of the states through a surface. So it's basically, again, we need to count states. So that's how the action works. And so let's sort of have an idea of how counting states work. First of all, in the discrete case. In the discrete case, you can imagine to have two variables here. The first variable is the shape, the second value is the color. And now you could have a set of different shapes, which would be different configurations for the first variable. And you ask how many configurations are there, and you basically just count 1, 2, 3, use the counting measure, and you're done. And again, I forgot to change the pointer because it's annoying. There we go. Okay. Same thing, I could have a set of, instead of states, which is this set V, which I'm now, it's not taking at one variable being equal. And then again, how do I know how many states I have? I count them, 1, 2, 3, 4. Same thing with degree of freedom. I have 1 and 2 degree of freedom, I count them. So in all the cases when I'm on discrete variables, I just use counting measures. Now, what happens when we go to the continuous case in classical mechanics? We count configuration using the symplectic form. So we have this surface S, which you should imagine as a two-dimensional surface in a four-dimensional space, which basically is a constraint on one of the degrees of freedom. And the way that you count how many configurations you have, you go and you basically do the surface integral of the symplectic form. So these are telling you how many configurations you have in this piece of surface. Same thing, if you have a volume, now you need to count the states, which are going to be the product of the configuration in all the independent degree of freedom. And so you are going to have a volume form that comes from the symplectic form, and that volume form tells you the state density. At each point, what is the density of states that you have. And so you can see that in both these cases, we're not using anymore a counting measure, because the counting measure would give you infinite. You have infinitely many points, but you're not really care about the points. You care about sort of configuration in some of states on a continuum. So it can't be just counting the number of points. But then you have finitely many degrees of freedom. So how do you count the degrees of freedom? You just use a counting measure. And so Hamiltonian mechanics in this context is the correct count of, gives you the correct count configuration states of finitely many dense, degree of, no, finitely many, no, sorry, Hamiltonian is correct count of finitely many dense. No, it's finitely many degrees of freedom. This is incorrect. Now, on a field theory instead, we are looking for something where the degrees of freedom themselves are dense. So the degrees of themselves are continuous, not just the possible configuration on each degree of freedom, but also the degrees of freedom themselves. And you have, in the same way that we have a principle of least action in particle mechanics, we have a principle of least action in field theory. And we would expect that if this was a flow of states, this probably is also describing flow of states. At least that's the simplest conjecture. And so this should be some kind of line integral of vector potential of the flow state density, maybe something like that, where you have not just a density of configurations, but you have a density of configuration per degree of freedom, right? So the number of configuration per degree of freedom is the thing that we need to get, such that we can multiply by the number of degree of freedom, and that's how we would basically count the state. So the idea is that if I have a volume and I double the sum of the volume and I have 1 degree of freedom for my field at each point, the intuition should be that if I double the volume, I double the degree of freedom. So it could be, it would be logic to assume that the volume form that we get in relativity, the volume of space, are basically related to how many degrees of freedom that we have. And since we read the Lagrangian as the Lagrangian, essentially the gravitational Lagrangian plus the matter Lagrangian, maybe the idea is that this gives us the flow of degree of freedom, and this is the flow of configurations within and across degrees of freedom. That could be something. And sort of the way that I picture in my head is that you imagine that you have a Cauchy surface. So this would be sort of a snapshot of the whole three-dimensional space with the field configurations on top. And then we want to evolve it. And now this point here will go here, and this point here, a space will go here. And so if the space is stretched, right, then it's like we are taking the same number of degrees of freedom and spreading it around in space in some sense. And if we are doing that, then you would expect the uncertainty or the range of degrees of freedom on each field to sort of shrink itself. So if I compress the degree of freedom, then I am expanding my number of configuration for each degree of freedom. And if I stretching the degree of freedom, then I am compressing the number of configuration in such that the product of the number of degree of freedom and the density of configuration per degree of freedom remains constant, because we want to have deterministic and reversible evolution. Therefore, the count of the configuration states has to be conserved, and it has to be constrained. So that's the idea, which seems a very reasonable idea, and it seems that it should work. And of course, I don't know enough of essentially field theory in a symplectic formulation and how to put information theory and all this to be able to do the work. And I hope that it can happen like it happened for the classical limit of quantum mechanics, that I can find somebody else to sort of complement, because again, really going through the literature, all of this by yourself without it takes forever. So I'd rather work on things where I can be more productive and wait for somebody to help me figure this out, so that we can move the project faster. So that's as much as I'm going to say with field theory. Then we can go and jump to thermodynamics, and there is the key idea in reverse physics for thermodynamics. Probably we have it identified, and we go through them quickly. And the idea that entropy in physics, it's really the count of evolution, the possible way that things can fluctuate, instead of being the count of macrostates and the count and some sort of information theoretic idea. The good thing is that under suitable condition, you recover those ideas from starting from the count of evolution. So things sort of make sense. And the idea of a statistical equilibrium, basically we can show that it should maximize the count of evolution, and sort of the thermodynamic equilibrium is where all the parts in statistical are in statistical equilibrium from each other. So, and again, this means that there is no information flow, that information went everywhere and so on. So you recover some of those ideas. And one of the things that comes out of this, that equilibrium is fundamental, is equivalent to requiring that the dynamics of the system does not depend on the internal dynamics and the environment. So we typically have in thermodynamics this idea that the equilibrium, you put something there and things stop evolving. More than stop evolving, I'd like you to think that the system now, the configuration of the system, it no longer cares what's going on at in the internal structure and in the external. So it becomes independent. And of course, if it becomes independent, it means that all this macroscopic quantity has to stabilize because it doesn't matter what's happening. So that's it. So in this sense, we're looking at thermodynamics as a more fundamental theory, in the sense that you kind of need this type of equilibria to be able to define a system. To be able to define a system, you have to say, okay, these are the variables that I care, and everything that it's in this internal structure and so on, it doesn't matter to me. And also what's happening in the environment, I can kind of define a boundary, and then that's what's happening, and that's it. I don't care what else happens on the boundary. And sort of the idea also, quantum mechanics becomes something like that, because you have the system, the internals are not accessible, you're not going to be dependent on that, and then you have some interaction with the environment, but even again, it's basically just noise. And sort of that's basically the idea. So more than just thermodynamics, this should give us something a little bit more general and a little bit more fundamental than just heat and work. It basically touches how do we create a system and subsystem, and what is the relationship between all this. So let me give you an overview of this, how it should work. And so this idea that entropy, that process entropy in physics, is really the logarithm of the count of evolutions. You start with the idea that you have a system with a state space, and you can think that is a classical microstate, a quantum state, or any state of a dynamical system that you have in mind, a bunch of variables with some numbers. That's absolutely fine. And then you're going to have an evolution. So you're going to have the state space of the system at a different time. And you are going to get an evolution, which is the complete description of the system at all times. So you know that it passes here, here, and here. And now we can define a process as essentially a collection of possible evolutions. So a process, you can think as something that constrains which evolutions are possible. So if you have a complete chaos, then every evolution is possible. You can jump from any state to any state at any time. So you have all the possible trajectories that you can imagine. But if there are some constraints, some forces, and something that is more reasonable, then some of these evolutions are going to be excluded. So that's it, that they just go away. So you can think it really as a process, as the space, as a subset of the space of all the possible evolution. And then what we want to have, what we can show, is that the description at each time corresponds to a set of evolutions. So if I say I know that at this time I am in this state, then I know that the process from the beginning to end will have to be going through one of these evolutions. And the thing that we're going to assume that we are going to be able to do is count the number of evolution for a particular state at a particular time with some sort of measure, which probably is going to be something more complicated. But for now, in this example, let's just pretend that it's just a measure. So I have a state, and then I say how many evolutions are compatible with the fact that the system at time t is in that state. And so I can have I can count the evolutions here, and it's 2, and I can go and look at the configuration here, and I say that's 2. And now you can just with this, you can start defining a probability, a conditional probability of having a future state given a past state. So, for example, if I want to say what is the probability that I'll end up in this state given at time t plus delta t, given that I was in this state at plus t, well, you say, okay, I have 2 possible evolution. Only one of them goes through this state as well. Therefore, this is just 50% of probability. And so the probability is the measure applied essentially to the intersection of the evolution that pass through both, through one and the other, and over the count of evolution of the count of evolution that pass through S0. So that's basically how you can define. And then you can say, well, okay, now I can define probability from this overall measure, and I want to define a process, a deterministic process. And a process is going to be deterministic if knowing the state at a particular time allows us to predict the state of the future time. So, for example, if I'm here, I know that I'm going to be here, and if I'm here, I know that I'm going to be here. And so for this process, these are the processes over which we can write a law of evolution. So you can imagine already if the goal of physics is say, oh, I want to be able to write the laws of evolutions in such a way, then you are restricting yourself to deterministic processes. And kind of that's why deterministic processes are so important in physics, because that's sort of, if we want to write this, we need a deterministic process. But there is something that is interesting between the interaction of this definition and the count, because in a deterministic process, the evolution can never split. They can only merge. So if I have 2 states and then the future state is the same, then from then on, the evolution has to be the same. So if we go through the state over time, we can see that the count of evolution per the state as the state evolves can only increase or stay the same. So here we go from one trajectory, from one evolution that goes through here, through 2 evolution that goes through here, 3 evolution that goes through here, and this goes in fact from one, right? So that's the only thing that you can do. It cannot decrease. Conversely, we can define a process to be reversible if knowing the state at a future time allows us to correct the state at a past time. And here you have the dual. The evolution can split, but that can never merge. So if we're here and these 2 came from the same state, then of course everything has to come from the state from then on. So now the count of evolution as we go through the evolution itself can only decrease or stay the same. And so now if you have a process that is deterministic and reversible, now this count of evolution, of course, has to remain the same. And so we have this nice property. Well, we basically said very little. We said that we have states and we have evolution and we know how to count them. And from that, we can already define a quantity that increases or stays the same, that cannot decrease if the process is deterministic, and it's equal if it's reversible, without knowing anything about anything. And now consider that we have a process where the system reaches a final equilibrium. And in this sense, we're kind of thinking of a dynamic equilibrium, but it also works for statistical equilibrium. And I assume that this final equilibrium can be predicted for the initial state. So you have a bunch of states, and then at some point they gravitate, they go towards one, and then once you're there, they stay where they are. So when you are in transition, of course, the count of evolution increases, but once you are at equilibrium, that's it. You've merged all the ones that you can. You can't merge anywhere, and so your count of evolution is maximal. And so now we have that for the deterministic process. We have the counter state. Not only it cannot decrease, and it's equal for a deterministic process, for a reversible process, but it's also maximized at equilibrium. And so now this starts really feeling like, well, this looks like a good candidate for entropy. But now one of the things that you want is, for entropy, it's important, what happens when you combine subsystems together. And if you are in the state space, what happens is that if you have 3 possible states for one subsystem and 2 possible states for the other subsystem, then you just get the product of the 2. And you always get the product. Now, if you are composing processes instead, the fact that you have 3 possible trajectory on X and 3 possible trajectory Y doesn't mean that when you put them together, you have 9 possible trajectories. Because there can be correlations. And so the evolutions in general are not the product, because there can be correlations. But if you assume that the systems are independent, that is, the motion of one does not really influence the motion of the other, then you have all possible combinations. And so not only the number of states becomes the product, but the number of evolution also have to become the product. So when you have the 2 subsystems, the condition on both subsystems becomes, the kind of evolution on both subsystems becomes the product of the individual subsystem. And this is, again, a maximal condition, because if they're not independent, you're going to have fewer elements, you can have more. And so this is not only the case of the independence that you have the product, but it's everything else is going to be below the product. And since we have this product, but we would like to have an additive quantity, well, what we can do, if we just put a logarithm in front of the measure, and then the product of the measure becomes the sum of the logarithm, and therefore the logarithm of the count of evolution becomes additive for independent system and becomes subadditive in all other cases. So now we can define the process entropy to be this logarithm of the count of evolution. We know that it's additive for independent system, and for a deterministic process, it can not decrease. It remains the same if it's reversible, and it's maximized at equilibrium. Right? So we really have now something that looks like an entropy. And then you say, okay, well, does this have anything to do with the type of entropy that we think in physics, like the information entropy and so on? Well, here is how you can recover the idea of the information entropy, the rho log rho. Suppose that a macrostate X is a dynamical equilibrium of the microstates. Basically, this X, like this macro state, is really all the possible ways that things can fluctuate and still keep the macroscopic variable the same. So the macrostate fluctuation can be characterized by a stable probability distribution rho of X in each small delta t. So the probability distribution that we have is really the probability of visiting the state in this small delta t. And again, every time that you define an actual system and you define measurements on those systems in thermodynamics, there is an implicit delta t, which is the time that it takes to take the measurement. So when you make a measurement of temperature, there are some things that needs to equilibrate. You need to explore the system. So there is already sort of a natural minimal time for the macro system to make sense. And so this distribution now becomes what's happening below that threshold of the macro state, what happens at the smaller scales. And now an evolution lambda t for the microstate, then you can think it as a dense sequence of infinitely many microstates, whose recurrence has to match rho. So you have your delta t, which is the sort of your definition that comes from your definition of macro state, and you can still imagine that there is sort of a continuous evolution there, and you pick countably many points along that evolution. If the evolution has to be continuous, those define, as long as it's a dense countable set of points, they define the evolution, because countably many a set of countably dense points are going to tell you what the continuous thing is. And the idea is that now the macrostate measurements cannot be sensitive to permutation of these macrostates. So all the possible evolution, such that the overall distribution of these samples matches the rho, is a possible evolution for the subsystem, and your macrostate processes should be independent of what actually is the realization of the macrostate. It shouldn't be sensitive, because we're only sensitive at the level above. And what happens is the Shannon entropy counts all possible permutation of an infinite sequence, which is delta delta t, which equals all possible evolution. So one way to define the Shannon entropy is to have a set of things and make all possible permutation on a sequence that goes to infinity. So you have a density of permutations, and that's exactly what we're doing here. So you recover the rho log rho by basically saying, I can think of the evolution of the macrostate as an permutation of uncountably many objects. So this is good, because it means so that we can recover what we want to recover. And so the idea is that this macrostate, this equilibrium at the macroscopic level, you can think it as a tube, right? And you're jiggling around inside the tube. And when we are describing, it doesn't matter which actual realization within the tube you have, because all you care is what tube you picked, and the tube is fully defined by the macroscopic quantity. And so the idea is that you can think of this equilibrium as the evolution decoupled from the environment and from the internal dynamics that are going to be responsible of the oscillations within that tube of evolutions, and that's basically what we're trying to do when we're describing this type of equilibrium. So if this works and if this makes sense, then we should know that we have no mention uncertainty, disorder, statistical distribution, lack of information when we define the basic concepts. And therefore, these concepts are not fundamental in this context. Actually, the thing that was fundamental was that we had a dynamical system, and without law of evolution, like not even a dynamical system, we had a system and a set of possible evolution and the ability to count them, and that was enough to define these objects. And then in different conditions, we found some properties, but the property in the sense at a fundamental level is just there are some possible evolutions of a system. That's it. We also have not discussed what type of systems or states we have. Therefore, everything we said in principle is valid independently of the type of system. And the goal here would be, the stretch goal would be to create a sort of a generalized type of thermodynamics that explains why a lot of the thermodynamics idea and information theoretical ideas are present in biology, economics, evolution, and so on. Like these concepts are being used a lot more than just in physics. And so having a sort of a general theory of why that is and what is it that it's describing, I think it would be nice. And then, again, the idea is that the process entropy increase, why the entropy increases in time, is explained by definitions and the setting, the fact that we have a process with equilibrium that depends on the initial state. And so this type of explanation, it's really a definitional explanation. We are looking for the things that has particular properties, and therefore we have these consequences. And the explanation is, to me, straightforward, because, as I said, all that requires is being able to assume that we can count these things, and there is no mechanism. So any mechanism for which you get a process that has this equilibria, and that gets the correct count in the same way, it's fine. So again, this sort of matches a lot of the other insight that we had in reverse physics, where a lot of the stuff that we got in classical mechanics, like the action principle, we don't have it because there is a process that finds the action. No, because it's just the expression, the re-expression of some other conditions that you've put on the process. So these are sort of all hodgepodge ideas, which it's exactly why they are open problems. But just to give you a sense, also this can allow it to recover the thermodynamics if we further constrain what are the states and the system that we're looking at. So if we assume that states are equilibria of faster process scale, then each state will have a well-defined entropy. If you assume that states are identified by extensive property, and you assume that this quantity is the energy, then you get the existence of an equation of state, because given these extensive properties that fully define the state, you need to have an entropy because the states are actually equilibrium. From these, you can define the extensive quantity. This is basically the Gibbs approach to thermodynamics. You have an equation of state in entropic form, you define the intensity quantities, and then you can define your differentials, and you can recover your usual relationship. And what you're actually doing when you're studying your heat engine with a reservoir and a mechanical system, you basically are trying to understand the interplay of energy and entropy. So you have a reservoir, and a reservoir is a special system where the energy is the only state variable, and the entropy is linear, is a linear function of energy, right? This function here is a line, and therefore all the energy is stored in an entropy. And so if you increase the entropy, if you increase the energy, you're going to increase the entropy, and so you have this this relationship. On the other side, the mechanical system, you have the same entropy for all the states, right? If you, no matter what you do, the mechanical system does not have a different entropy, because you need to be able to put the energy in and get it back, so that the entropy cannot increase. So there is no energy that is stored in entropy. And if you were to calculate the beta for this, right, because the beta is simply the derivative of the energy respect to derivative of the entropy respect to energy, and since the energy is the entropy is a constant, this would be zero. So in this thermodynamic setting, the mechanical system is like it has infinite temperature, and therefore you can take something from a mechanical system and put it at a reservoir because you're going to a lower temperature, but you can't always do the reverse, because it would be like taking something at a finite temperature and put it at infinite. And this also tells you why sort of negative temperature, the betas that are negative are sort of very difficult to see, because the mechanical system now is lower than has a beta that is lower than temperature, sort of in some sense lower than all the other negative temperatures, and so all the energy now wants to go to the mechanical system and get out of the states with negative entropy. So anyway, this can be done. You can recover things, and so if there is anybody interested in helping me figuring out how to clean up all this stuff, that would be great. Now, the other part is, of course, quantum mechanics. And as I said, in quantum mechanics, we have ideas that are a lot more well-defined than we have in the thermodynamics. So it's clear that irreducibility and lower bound of the entropy is the only ingredient that makes quantum mechanics different from classical mechanics. The problem is show it in a clean way, and that's where I don't even know whether we have the correct math to be able to do that, so we sort of have to become a little bit more inventive. So the goal here is essentially to develop a minimal interpretation that is based on what and only what can be settled experimentally. So no talk about hidden variables and multiple worlds or whatever people like to talk about. What everything has to come out of is that states are ensemble, either pure or mixed, at some sort of equilibrium where the internal dynamics and the variables can be ignored. So and that's essentially what puts this lower bound of the entropy, that if you were to go and know more about what's happening and get a more complete description, then you would have to know about the internal dynamics and the environment dynamics, which you said you can't explore, or it's completely independent, and therefore you can't really get any information about that. The core, the gist of everything is that projection, you should really think them as process of equilibrations, and we'll see why. And that unitary evolution is deterministic and reversible dynamics, which can also be recovered as a quasi-static evolution. So you see, I'm talking about, I'm using terms that are very close to thermodynamics to actually describe quantum mechanics, which is kind of the point. We should be using and recovering quantum mechanics and not from like very strange ideas. Like this is the problem that I was saying 2 days ago. There are this is similar in spirit of what many people do with reconstruction of quantum mechanics. The problem is that if you go and look at at least all the reconstruction that I've seen, at some point they have some mathematical requirement that it's not clear how you would justify from the physics. And here we're striving to use only physical concepts that are already there in our physical theories, so that we have a nice intuition for those, and sort of they work, they make sense. And I do think that all the elements are there, scattered in all the different papers and videos and notes. They just need to be all put together. So let me tell you a little bit how it works. So in quantum mechanics, projections are very important, and mathematically projection is a linear and idempotent operation. That's what defines a projection. Now, imagine that we have a process like the measurement process, right? You have a state that comes in, and then you have the possible eigenvalue of your measurement, right? And you go there with a given probability, right? This process is linear in probability, in the sense that if I have a mixed state, then I can decompose the mixed state into pure state, apply the process on each of them, and then sum the output. So the process of the measurement process on the mixtures is equal to the mixtures of the output of the measurement process. Now, what does it mean that it's a projection? It means that if I repeat the process, the same thing that I had at the beginning, I get exactly the same. So I get the same result, meaning that a possible output of the process, if put again through the process, it gives you the same thing. And again, we already have a name for a state that if you put that is unchanged by a process, which is an equilibrium. So a measurement process is something where all the outputs are equilibrium of the process. And now you can also reason it in the opposite way. If you have a process such that all the outputs are equilibrium of that process, that's a projection. So instead of thinking of measurement as projection as measurement, and measurement being special, you should just think as measurement as projection, as processes whose output, all the outputs are equilibrium. Therefore, a projection is an equilibration process, and a measurement is also an equilibration process, because you want the output to be stable, to be sort of and the measurement process to be repeated. And again, we are talking about equilibria. Can we make a parallel with thermodynamics and statistical mechanics? And of course we can. So suppose that you have an open glass of water. The number of particles is not well defined because it keeps fluctuating, but the chemical potential, the volume, and the temperature are well defined. But now suppose that you want to have the number of particles well defined. How would you do it? Well, you put a lid, and now putting a lid on changes from a grand canonical to a canonical ensemble. You are going to have a probability to end up in one of these things, but then when you are in one of these states, you know that the number of particles is now fixed. But once we fix the number of particles, the chemical potential is not defined anymore, because the chemical potential really tells you how the system is fluctuating, and the system is no longer fluctuating in number of particles. Therefore, the chemical potential makes no sense to be defined. And now you can compare this to what happens during a spin measurement. You prepare a particular direction of spin, meaning that you have put the system in an environment where there is a vertically aligned magnetic field and the thing has equilibrated and now it's pointing up. And now you do a spin measurement. What does it mean that you spin measurement? You change abruptly the magnetic field. Essentially, you change the boundary with the system, and you're forcing the system to pick one or the other. And once the system has picked one or the other, it has to stay where it is. So this is the same thing. At the beginning, there is one variable that is defined here, and there is one variable defined here. You force the system to change abruptly, and now you're going to have a different set of variables that are well defined. And so the idea should be the quantum constants are just different boundary conditions. And what you're doing during the measurement, you're doing something that is akin to what happened in thermodynamics. When you change the type of equilibrium, you have an abrupt change of the boundary condition. So that's one type of evolution. If you assume that you have a unitary evolution, that you want to something that is deterministic and reversible, what you find from simple calculation is that you were going to have a Hamiltonian that tells you how the system is evolving, because the change of the system has to depend on the previous state of the system. And in this case, the final state has to be normalized, and therefore you get that the time evolution has to be, the generator of the time evolution has to be an Hermitian operator. So in general, then, you can imagine that any process, deterministic or stochastic, has to be linear in terms of the ensemble. Whatever statistical mixture we put in, the output has to be the statistical, the mixture of the outputs. And you're going to have two types of processes, one that are deterministic and reversible, that gives you this unitary operation, and other ones that are equilibrations, and which are projection. And both of them are idealizations, in the sense that deterministic and reversible evolution means complete isolation, which you're never going to have. And also equilibration, and maybe it's something idealized. It doesn't really work like that. There is something in between. But in some cases you use one, and in some cases you use the other. And in this sense, since both are idealization, it's not that one is more fundamental and one has to be reduced to the other. In this sense, there is no measurement problem, because there's no question as how nature chooses which process it has to use. Nature does what it does. We have these two models that are idealized, and sometimes we use one, and sometimes we use the other. Now, what is more interesting, though, is that when you define the Hilbert space itself, you are mathematically defining all projections. So mathematical Hilbert space is a Banach space plus the projector on each subspace. So there is no, technically, when you're defining a Hilbert space and your state space in quantum mechanics, since you have an inner product, you may not define a deterministic and reversible evolution, but you are always defining the equilibration. So you are always saying that there is a projection for each subspace, meaning that there exists a way to equilibrate every, to make so such that every state is the output of some equilibration process. And that basically tells you this idea that I was saying before, recovers this idea that every state is some sort of equilibration. And what you can do is that you can recover unitary evolution as a sequence of infinitesimal projection, and basically as a quasi-static evolution. So the way that you can think then quantum mechanics is you have some states. States are outputs of black boxes, and your black boxes are these equilibration processes. And then you put them one after the other, and you make this quasi-static evolution. And this also makes sense to what you do, for example, in field theory. In field theory, to calculate the scattering processes, you put the initial state at minus infinity and the final state at plus infinity to describe something that takes far less than a femtosecond. So it's clear that you are substituting the real process with some other process, but these are the type of things that we also do in thermodynamics, and so it makes sense that this picture sort of agrees with what we're doing then at this level. So So this is basically the idea. We have black processes with equilibria that allows you to define states, because states are equilibria. You get the projection, you get the state space, you do a quasi-static evolution, you get deterministic irreversible evolution, and from that you get unitary evolution. And so you have that every preparation is a measurement, and so time evolution prepares the system at each time. So it's like, I prepare this state, but then time evolution is going to prepare the state at each of the other steps. And so if we think about these projection, not just as measurement, also preparations, then time evolution is a series of measurement and a series of preparations, because each preparation is a measurement, and all of this sort of can be made self-consistent. So that's what we are shooting for. And of course, as I said, there are lots of other details to be fleshed out, but I do think that this makes the whole thing all consistent without using a lot of the weird things that comes out in the foundation of quantum mechanics. So since the time is running out, and there are probably going to be lots of questions on this anyway, we can go at the last few things. So for quantum field theory, as I said, we should first do quantum mechanics and classical field theory before talking about this. But I did want to sort of continue that idea of counting the states, because I think you might have some insights of what needs to happen when we quantize. So let's see if okay. So one of the ways to show that sort of a lower bound on the entropy has to break, in some sense, the classical ways of thinking about states and so on, comes from this sort of problem. Suppose that you want to count states on a continuum. So you have a real line, and you want to count the number of configurations on the real line. Now, you would like to say that each state is a single case. Each point on the real line counts as one possible configuration. You would like to say that a finite continuous range, since it carries finite information, will have finitely many configuration as well. There is 1 meter worth of configuration. You would also want that the discounted configuration is additive over disjoint sets. If I have a set here that it's 20 configuration, and a set here that it's 200 configuration, and they're disjoint, when I put them together, I get 220 configuration. Now the problem is these are clearly incompatible, because if every every configuration counts as 1 and a finite range has to be additive, you would get that the finite range has infinitely many points, and therefore it has an infinite measure. What happens in classical mechanics is that you discard either the first one or the second one. If you discard the first one, you get a Lebesgue measure, which is what you typically use to count configuration of a continuum. And if you discard the second, you get the counting measure, which is what you use to count configuration on discrete sets. The problem is that what you do in quantum mechanics instead, you must give up the third one. That's sort of what happens. So if you imagine that you have the Bloch sphere, right? As we saw in classical mechanics, you count the configuration with the logarithm of, so the entropy is the logarithm of the count of configuration, and as we saw before in our presentations, you can also define the count of configurations as the exponential of the entropy. So if you do this in quantum mechanics, if you get a point, each point, right, each point A and B, would have on the sphere, on every pure state, has a 0 entropy, therefore the exponential of 0 is 1, so every point will count as one state, which is what we want for the single one. And if you count, if you get the whole Bloch sphere, right, the Bloch sphere has the maximum entropy that it can give is given by the center of the Bloch sphere, which is going to be 1 bit of entropy. So if you take A and B and put them together and make a mixture, you can reach 1 bit of entropy, and therefore 2 to the 1 is 2. Therefore, the set of A and B now counts at 2 states, which makes sense. You have 2 orthogonal states, they are perfectly distinguishable from each other, and that's what you get. Now, if instead you take 2 elements that are not orthogonal, then you can't get the full one bit of entropy, you get less. Therefore, the count of configuration is less, if we use this measure to get it, it's less than 2. So the idea, again, that the set of A and B gives you two completely distinguishable number of states at everything else being equal. But A and C, if you take two things that are not orthogonal, then they're defined in different contexts. These states are defined in different contexts. So they are different states, but they're not completely distinguishable from each other. So they don't really count as two complete and indistinguishable states. And this is sort of how quantum mechanics solves the idea that we want the states to count as one, but we still want to have a continuum such that we can transition from one state to the other in a way that it's it's smooth and differentiable and so on. And so this is why sort of all the probability feels weird in quantum mechanics and so on, because you're losing this additivity property. Now, what happens, and this is again the conjecture, is that you're going to have the same problem if we want to have a measure of number of degrees of freedom and counting the number of degrees of freedom as region of space. So again, since we have a degree of freedom in a field theory, every degree of freedom in a point, we would like that every point is a single degree of freedom. We would like to say that at this specific point in space, there is 1 degree of freedom. And again, we would like finite volume to have finitely many degrees of freedom and the measure to be additive. And we are going to have the same problem that we would have, we were having when we were counting states. And therefore, it's not like in the transition from classical mechanics and quantum mechanics, it's very destructive because you have to change this idea of additive measure. It's very likely that you're going to have the same problem if you want to put a lower bound on the degrees of freedom count, because it's not going to make much sense that in a region of space you have less than 1 degree of freedom. And so what's going to happen, in the same way that the states should be counted if they're distinguishable, and you have two states that are not fully distinguishable, and therefore they're not really two states, the measure does not count them in two. Something like that should happen with points in space and degrees of freedom. If I have 2 points in space that are very distant from each other, then yeah, the configuration of one is going to be independent from the configuration of the other, and then we should say, okay, those are truly independent degrees of freedom. But if we put them closer and closer and closer, at some point, you're not going to be able to say, oh, yes, these points are independent. At some point, they are going to basically become the same degrees of freedom, because they're so close to each other, and you're not going to be able to put something different on the others. There's going to be a strong correlation between that, and they're not going to be independent. So if we want to really have a lower bound on the number of states like we have, and therefore a lower bound on the entropy like we have in quantum mechanics, it would make sense that if we want to have a count of the degrees of freedom as the volume, we are going to have a problem to just use a Lebesgue measure for the count of degree of freedom, because you do not have a lower bound on the number of degrees of freedom. And so the conjecture here is that maybe this is the conceptual problem that you're going to have when you're trying to mix quantum mechanics and a proper field theory that does all of this. And it should make sense that it's a lower scale that you're going to have this problem. And so this is sort of a conjecture that I have, that if while we are building the whole in physical mathematics, the theory of ensembles, I'm always watching out for this problem to understand how this can be solved and if it can be solved. Okay, so basically these are a bunch of things that are still need to be figured out. And if you're interested in building a conceptual framework that treats physical theories, models, and physical and nothing else, and you want to help, I'm always looking for people to help. The simplest thing, if you have a particular knowledge in any field, if you plan to build the knowledge in a particular field, or even if you want to say, I'm just going to help review material So we have a form on our website, if you go to help contribute, that you can fill in and say, these are the things that I'm interested in, these are the things that I can help with. And then when I'm going to do a live, when I'm going to do something, or I have a problem, I can contact you and say, okay, let's go and discuss this. And then if you want to be more involved, then I'd suggest that you join the Discord server, and we can start interacting more to see what can be done. So that was the hour, and that's it. Open up for questions.
There are already a few in the Q&A. From Carlos, for classical field theory, my intuition is that everything that worked for point mechanics should translate according to the following correspondence. Position becomes field, conjugate momentum becomes conjugate momentum of the field, time becomes event, and integral on time becomes integral on a region of space-time. Is this incorrect?
It's a little bit more complicated than that. So for the conjugate field, I found two formulations. One that has a single conjugate field, one that is a vector of conjugate field for each of them. And the one that has a vector for each of them actually might my nose tells me that it's the one that works that is more covariant, because what you need to do, remember no, because you haven't seen it. The way that we recover the structure of phase space is that you have this relationship between position and momentum, such that position defines the unit, and momentum is defined as the units of momentum are the inverse of position. So Q defines the units and P have inverse units. So when you multiply them, the unit disappears. So you have a unit independent quantity, and that is going to be the counter state. So you have a counter state that is independent on the units that are being defined. Now here we have three things. We have the unit of the field, we have the unit of conjugate, and then and these sort of are going to tell us, as I was saying before, some kind of density of configuration per degree of freedom, because then we need the volume and we need to multiply the volume. And so the question is, where does the unit of the volume go? If it goes so the idea is probably is going to be on the conjugate field. So you have the field that defines the unit of the configurations. You have the volume that defines the number of degree of freedom. But again, it has to be a volume in space, because time is not going to give you more degrees of freedom. And then you need a conjugate, and the conjugate needs to sort of cancel out both the units of one and the unit of the other. Meaning that if you have some change of units in the volume, the conjugate field also should change. Like if you stretch the volume, then the conjugate field should shrink. So these are the things that are absolutely not clear to me on how they should work. But I know that from unit consideration, they should kind of work like that. So these are the pieces that need to be figured out. And again, the standard math does not show these things, because the standard math takes the units and throws them out and pretends that they don't exist. Instead, all the things that we were doing in reverse physics, all the insights that led to those things, is because I was taking care of the units. And so here I need to understand what happens to the units so that I can have a count of configuration that it's independent of the units of the field and of the units that we give to space and time.
Right, the next question is from Thomas Oudeville regarding the evolutions, count of evolutions. I find this quite surprising. In an ODE, the curves can never cross each other or merge. Do you consider different kinds of evolutions than usual?
Right. So if you have an ODE, you have some type of deterministic reversible scenario, right? For every point, you have another point. And so in that case, these are the things that need to be, as I said, that need to be understood, and because what we showed were example in the discrete, how everything needs to work on a continuum is a little bit to be understood. So in an ODE, you're going to have also the problem that solutions can converge to a point. So they don't intersect, but they become more dense. And I do think that the entropy should qualify that, should understand that, because at the end of the day, what you're looking is areas and how they shrink and so on, right? When you have a dissipative system, right, in classical mechanics, there is an ODE, the thing spiral maybe at an equilibrium. It's not that they actually go to the equilibrium, but you get denser and denser around the equilibrium. So these are the pieces that needs to be fully understood.
Next question is from Tobias. A Hilbert space is a Banach space plus all possible projections. Mm-hmm. Does that require completeness, or is this just defined through the inner product?
Defining the inner product means having all the projection. It's exactly the same thing. So the completeness is given by the Banach space. So Banach space has a norm, and the topology is complete with respect to the norm. Then you're adding what's it called? An inner product that is consistent with the norm. Therefore, if you were incomplete with the norm, now you're complete with the inner product, and you're adding all these projections.
Next question is from Xinyue. The slide seems to suggest that we can reconstruct Shannon entropy without probability distributions. How to understand this?
No, you need the probability distribution to reconstruct the Shannon entropy. So what you do for the permutations is you have a probability distribution over some elements, right? And then you have you do a choice of countably many by picking one at random according to the probability distribution. So if you have, let's say, something simple, you have head or tail, right? And then you sort of flip, you have 50% to get one. You imagine all the strings of a head or tail taken at random from that distribution. And then you basically go and count them and do, you basically count them for any n, and then you make the n go to infinity. And you're gonna get the density of the states. There is something wrong going on with my screen right now. I'll fix that later. Okay, I lost the slides. So that's basically how it works. I have a video on YouTube that actually goes through this definition, where I have all the like the 3-4 different ways that I can recover the Shannon entropy. One of them is through the permutation. So you can go and look at that if you want all the details.
So the next question is from Daryl. Are you taking PhD students? It has been upvoted. And
yeah, I'll leave that to the professor to respond to that.
You're leaving it to me. So the primary issue is funding, really, for this research, as you might imagine. There isn't really government funding that funds this type of very foundational work of revisiting the very low-level foundations of a lot of existing theories. So yeah, right. We do have an external grant right now, but the funding situation is very limited. So that's basically the main constraint in taking on PhD students formally through the University of Michigan. There could, in principle, be possibilities working with others who are primarily affiliated, who are getting their degree issued and financially supported through another institution. And we would be able to work with them potentially if we found a project of common interest that would be acceptable to their home university. So that could be a possibility. And of course, we're trying to find other sources of funding so that we can expand opportunities in the future and just get more people involved. As Gabriele has been saying, we really need to build up a larger community. It's really large, ambitious project. So we need more people to be involved to carry out this program. I see there's a follow-up. What about undergrads at University of Michigan? That is much easier. since undergraduates can do research for credit, so we do that relatively often. Work with undergraduates for typically for research credit. And we've had I guess two so far officially do their senior theses or honors theses on the project. Tobias points out that he is currently a PhD student working with us here at the University of Michigan, who originally found the project through YouTube, and a couple years later reached out.
So in principle, we do take PhD. The problem is that you might have to teach to get the what's it called, the support, and there are all these details that, again, Christine knows more than me.
Those are all the questions in the Q&A.
So I'm happy to talk more about anything. So if somebody wants to give me a topic, I'll start talking. So.
Skip the slide. Robbie asks, how much topology should I know to pursue fundamental physics?
How much? Is that the question?
How much topology?
How much topology? Good question. So for me, the main problem is not really knowing like deeply about the subject, in the sense that topology quickly becomes a lot of things that we're never going to be interested. So just to give you an example, topologies are also defined on, so the topology that we are interested in are all T0 and second countable. There is a lot of work on other topologies that are not second countable and not even first countable, right? And there is a lot of literature about that. So you're going to be interested in that? Absolutely not, right? So it's very particular what are the things that we should be interested in physics and what shouldn't we? And part of my problem was, when I started working on this more in detail, was basically that. Should I be interested in that? Should I not be interested in that? And that's where, going both from the physics and both from the bottom, you start having a clue. So for topology, for me, the thing, it's funny because I only understood, for example, something that I think everybody should understand, like a month ago, which is the connection between topology and limits. That would be a much better way for if you're doing physics to understand topology, because understanding there's a notion of limit instead of all the other things that are said would allow you to understand what it actually is, because a lot of the time topology is used in physics as basically the things that allows you to count holes in a manifold. And that's not how mathematicians think of topology. And then there are issues that there are tricks that you can do in topology, that it's a little bit like taking, I was saying that taking real calculus and taking a real integral and transforming a complex variable and do the calculation there because it's more convenient, right? So there are all these tricks that have to do with compactification in topology that are very important in topology. There are lots of results on those things. And again, if you're doing a calculation, maybe they're going to be useful. But then if you want to have this idea that, I want the math to be meaningful and I want these things to actually be something weird, then you realize that a lot of those tricks are like you should never ever do them. So the compactification is basically this idea that you take a space that it's not compact, which means essentially you can't always cover it with finitely many pieces. Essentially, that's the way that you can think about compactness. And you add some points, and then magically the thing becomes compact. So, for example, the circle is compact because if you have open sets that cover the whole thing, you can always do it to be finitely many open sets, open intervals. Now, the real line, instead, it's not compact, right? Because you cannot always cover. If you start with countably many sets that cover the whole thing, you can't throw some out and get the finitely many. You always have infinitely many. But you can understand the real line as a circle if you add a point to infinity. So now you have compactified the 1 point compactification of the real line is the circle. But adding the point of infinity in physics, you would be like literally saying that infinity is a possible value for your variable, right? Which of course that doesn't make much sense. And so the issue for me is really understanding when these things are mathematical tricks, when they have physics in it, and so on. And again, you don't need so much. Like it's a different problem than the mathematician does. So if you go and follow a course in topology from a mathematician, this is going to tell you all these different things, all these different tricks, and so on. And I kind of feel that we should have a sort of a class where, as a physicist and engineer, so you're taught the bare minimum of what these things are and how they apply to sort of conceptually to physics and so on. And that's basically what we should have. And it's very difficult to do now, because if I tell you, oh yeah, you should definitely know some topology, right? And then you say, okay, I'll go and get a 2-semester class in the math department, so I really know topology. That's probably an overkill. But it might be that you need, pieces from the first semester and pieces from the second semester. That's kind of so. What I do for all these things is I take math books, like sort of I go through them quickly to just get some idea of these are the pieces that I need, and then I go and study the particular chapters that are needed. And it's the same for everything else. Order theory is the same thing. Like you need to understand some, because it's one of these fundamental things that keeps recurring, but it's difficult to say, oh, you need to know order theory or topology like a mathematician. So
I can add to that. I think long term it would be valuable if we had more people involved in the project to create a textbook, basically a mathematical methods in physics textbook that would be oriented toward the assumptions of physics program. Of course, you still need other things like, vector calculus or, although I guess we would teach that a bit differently. So it's not that you don't need the materials typically taught in a mathematical methods for physics class. We typically have those types of classes, at least in the US system of physics education, where you do exactly that. You say, well, you need to know some of some particular mathematical topic, but you don't need a full semester course in the mathematics department on that. So we're going to do 2 weeks on this math topic, 2 weeks on this topic, 2 weeks on this topic. So we would want to redo that course for in line with the assumptions of physics project, or expand that course.
And if we had people, if we can build a community that helps us build that, I think that would be very valuable.
Yeah, that would be valuable. That's definitely an area where I could imagine other people coming in to contribute, because it's basically taking the ingredients. They don't have to develop new ideas or new math, right? It's really organizing, identifying exactly what topology is needed, what measure theory is needed, what order theory is needed, and writing it up succinctly aimed at physicists, students in physics. And Thomas Sartoni has a direct follow-up on that, so let me skip to that. More in general, what mathematics is actually necessary for fundamental physics? As a beginning student, the landscape is so vast, it's hard to get oriented in it.
Yeah, not just for a beginning student, for everybody. And what happens is that people sort of just ignore the math that they're not used to, or they don't immediately see. Yeah. I mean, that could be, I mean, so for all these things, if people are interested, we could start having live discussions where you're not actually in a chat, you're actually live, and we can talk more with a bigger bandwidth, and start making the landscape. And I can tell you, look, these things are certainly pieces that you need. These pieces are certainly pieces that you need. These you should be aware that they exist, such that you at least know why you're not interested in them, right? So, for example, all of the definition of how infinity is defined in terms of ordinals and cardinals, I think you should know about that. But you should know about that not because it's important. You should know about that because you know exactly why it's not important. And even that is important if you're doing fundamental physics at this level, to know why and what is it. Because like I hear talks of people that present at conferences that clearly don't understand these things, and they say such nonsense that you should at least have the background to see that and say, okay, that's not going to be interesting. Because otherwise, the issue is that you might get fascinated, all these concepts and so on, and then you're just going to waste time.
Shinue has a question. In the quantum mechanics part, we seem to have quantum measurements being understood as parallel to thermodynamics measurements, but how does this resolve different observer issues?
So there is no issue of different observers, in the sense that the only thing that can, so this is where, again, there is a fundamental confusion on the role of entropy and the role of probability in physical theories. So yes, you can use probability to have expectation in the sense of credence and all of that, right? And but that's not what physics is about. I mean, if there is a measurement and one measures something, everybody else measures the same thing. Now, you're going to have the problem of incomplete information, in the sense that there is some kind of mixed state and I know more than you, right? But that just means that if I have my mixed state and you know more than me, you know you have a distribution that it's sort of a component of my distribution. So my distribution is your distribution plus something else. Since both classical mechanics and quantum mechanics are linear theory on the probability distribution, and so therefore mixtures of evolution is evolution of the mixture, there's not going to be a problem either on the unitary evolution or the projection, the measurements, the equilibration. Everything is going to work. So there is no sense that that people have to see different things. Now, there are all these other issues of Wigner friends and all of that, and Schrödinger cats and all that. But also all of those become moot when you understand that, again, there are quantities that are defined on ensembles, like temperature, like average energies, and all these things that are the macroscopic quantities. There are not things that can be in superpositions and stuff like that. They're just averages. You can't make a superposition of averages. It just doesn't make sense. And so a lot of the problem that come out from interpretations as they all come out of multiple observers and so on. Or they all come out because you are trying to give the mathematical object some meaning that it's problematic. And so one of the problems that you're going to encounter, for example, if you take the pure state as being the complete specification of one system, so one instance of a preparation at a particular time, you're going to come, you're going to get into all sorts of problems. But if you say, like we want to say, that even the pure state is an ensemble. So when I say spin up, I have the state spin up, it's not that I have the full description of a particular system. I'm still talking of the output of a procedure that always prepares this state called spin up. And so in that case, yes, my spin is always up and so that quantity is always well defined. But the preparation of all the other observables, there's still variability there. In the same way that you prepare your macro state with a particular chemical potential or particular temperature. A particular temperature, yes, the temperature is set, but the energy is fluctuating within your small delta T. And so it's not that everything is defined. You have an ensemble, and the ensemble is this infinite collection. And therefore, this variability that you have, you can think it as a variability in a small delta T, and sometimes it's a variability in a small delta T, but sometimes it's just a variability that, every time that I prepare the same thing. And so once you start looking at things like that, a lot of the problems that people have, to me, they sort of disappear. And part of doing the reverse physics and this minimal interpretation for quantum mechanics will be to do the due diligence, to go to the literature and philosophy and say, okay, all these problems are the people that claim that there is, and you say, okay, in our interpretation, in our setup, this doesn't apply because of this, so this is resolved like that, and so on. So that becomes sort of detail. But my main intuition is that all these things are going to resolve themselves.
Daryl asks, if we lose additivity, we no longer have a measure, right?
Yes, you have these things that are called the non-additive measures that are weird because a measure should be additive, but there's a field called the non-additive measure theory. And it's very developed in decision theory, fuzzy logic, fuzzy sets. They all use non-additive measures. We were hoping that the type of non-additive measure that we are interested in were those types, and it turns out that they aren't. So basically, it's another piece of math that I think we're missing to be able to study these things.
They're also more generally called set functions, right?
Set function is sort of the proper term for any function that you give it a set and you have a number. Then typically you want these functions to be at least monotonic, and so that if the set gets bigger, the number cannot get smaller. And these are sometimes called the capacities, as you will see later, because we call them capacities, but they are also called fuzzy measures or non-additive measures.
Thomas asks, would you be open to get me in contact with Jacob Barandis from Harvard? I plan to work on his recent research topic soon.
I already tried to contact the guy. So I saw his presentation on his stuff like years ago. And I had some technical questions because I didn't understand at a measure theoretic level what he was doing in probability, because he's doing probability like a physicist. Probability is a function that I integrate over, it's a probability density, but then that doesn't tell me some things. And he wasn't able to answer my questions. Then I also tried to reach out to him again. What was it? Last October, because he was supposed to be at a conference that I was also going in September, but then he wasn't there. So I tried to reach out because I still wanted to understand it. But then, yeah, he sort of disappeared again. So.
A question from Arno. What are your thoughts on the paper by Professor Renner? Quote, quantum theory cannot describe the use of itself.
So I don't know that paper, but I know of a lot of people in philosophy that that try this thing of, can you describe the fact that you're making measurement in something, so this circular thing. I do not know whether that's a valid question in general. That's my problem, in the sense that, as you saw before, the theory, any physical theory, you need to define a system and an environment. You're going to have a boundary between the system and the environment. In thermodynamics, it's always clear that you have a boundary in the system and the environment because it's part of the specification of the system. My argument is that even in quantum mechanics, you have a boundary between a system and environment, and that's the context, right? So the quantum mechanics is contextual because the context, because you need to define the relationship between system and environment, and during the measurement, it's more important because the measurement is something that is happening in the environment that is going to push the system in particularly defined states, right? And so if this is the case, and you also consider field theory something like that, I have a region of space, and there is all this stuff like that. I can't see anyway at a conceptual level what it would mean to close it in that sense, so that the thing can describe itself. Because clearly, quantum field theory cannot, if this region under this constraint of an environmental boundary cannot tell me what's happening outside, because I made the cut. I'm only describing the system under these conditions. So to me, it's a whole can of worm that it would need to be well specified, but quite frankly, it's one of those picture battles, right? I only have finite time, and I'd rather spend it into figuring out the things that to me have a much better chance to be solved and addressed than these other problems that I don't even know if they can be solved.
We are at 11:31,
Yeah.
so to move on to the last lecture.